Hello and welcome to Live at PALS. Today we will go over a chemistry IGCSE paper. Specifically, we'll be looking at the specimen paper from 2023, the alternative to practical paper, paper 6. Just a quick word in the beginning for the new syllabus that starts in 2023. I'm of the opinion that this paper has gotten quite a bit easier. Because you are not required to memorize all the chemical tests anymore for anions and cations in solution, the flame tests, and so on. Now you are given tables with all these tests and their results at the end of the exam on the last few pages. So that's made it a lot easier. You don't need to memorize all these things anymore. So yeah, so we'll be looking at this paper and let's get started. So the first question here is, student investigates the rate of reaction between magnesium ribbon and excess dilute hydrochloric acid by measuring the volume of gas produced. The student uses the apparatus in figure 1.1 to do two different experiments. We can see the apparatuses here, and first thing that we have to do is we have to name the apparatus. So make sure that you, before you do this paper, just memorize the different names of the different apparatuses that you need to know. You can find lists easily online for that. I think this is pretty easy here. These are not too difficult. X is a conical flask. Now, if you're not a native speaker, then it is called a conical flask because of its shape. This shape in general is a cone, so therefore it's called a conical flask. Y is a measuring cylinder. And here as well, now the shape itself, this kind of shape, is a cylinder, so therefore a measuring cylinder. The gas made in the reaction is hydrogen. Describe how the student can test that the gas is hydrogen, give the expected result for the test. So yeah, I'm pretty sure you know this test. This is probably one of the first tests you learned about in chemistry. And obviously this is the test where we use a lighted splint. And when we come near the test tube that contains the gas, this will give a squeaky pop. So the second part of the question, figure 1.2 shows the results of each experiment, so rate of reaction, and in figure 1.2 to determine the total volume of gas made in each experiment, and we can see we just simply, so here we have the time, and we can see on the y-axis we have the volume of gas produced, so we just go to the maximum and we draw a line over. Just do this in the exam as well so that the examiners can see how you got to your answer. Just use your pencil and draw a line from the highest point where our line goes horizontal over to the y-axis, and we can see that in experiment 1, which is up here, 80 centimeter cube are produced, and in experiment 2, 40 centimeter cube are produced. Now always have a quick look at the units. If that matches as well, that's fine here. So yeah, 80 and 40 centimeter cube. Use your answers in CI to suggest what the student changed in experiment 2. So let's go back quickly and have a look what the experiment exactly was. Now student investigates the rate of reaction between magnesium ribbon and excess dilute hydrochloric acid. So hydrochloric acid is an excess, which means all of the magnesium will react and some hydrochloric acid will be left over at the end of the experiment. Since the acid is an excess, that means we have to change something about the magnesium ribbon, since that is what's completely reacting. And we can see that in experiment 2, half the volume of hydrogen gas is produced than in the first experiment, and therefore the student has probably halved the mass of magnesium that is reacted in this experiment. So the student So on figure 1.2, sketch the curve expected in experiment if experiment 1 is repeated using magnesium powder instead of magnesium ribbon. All other conditions are the same. So if we use powdered magnesium, then the magnesium powder overall has a larger surface area than the magnesium ribbon. So therefore more of the magnesium is in contact with the acid. So there will be more frequent collisions and therefore the rate of reaction will be faster. But since we are not changing the mass of magnesium, our curve has to level off at the same maximum volume of hydrogen gas being produced. So that means our line must initially be steeper, something like this, and then it curves and levels off at the same volume as the first experiment. So make sure that your initial line is steeper. That's what we get 1.4, and then the second point is that it levels off at the same volume of 80 centimeter cube, but again it reaches that volume earlier than in experiment 1. So question 2, here we have to do some readings. The student investigates the reaction between dilute hydrochloric acid and 2 different aqueous solutions of sodium hydroxide labeled solutions A and B. Experiment 1, the student rinses a burette with dilute hydrochloric acid, fills the burette with dilute hydrochloric acid, runs out some of the acid so that the level of the acid is on the burette scale, and uses a measuring cylinder to pour 25 centimeter cube of solution A into a conical flask. He adds 5 drops of thymol phthalate indicator to the conical flask, swirls the flask while adding the acid from the burette to the conical flask until the solution just changes color. In experiment 2, the student empties and rinses the conical flask with distilled water and repeats experiment 1 using solution B instead of solution A. So this is a titration experiment, and here we have the volumes of the initial reading, which is 4.1. It's here, experiment 1, initial reading, final reading, initial reading 4.1, final reading 29.5. no, wait a moment. Now I'm mixing things up here. So experiment 1, final burette reading. This one, 29.5. And initial burette reading, 4.1. Okay, now we got that. Experiment 2, final burette reading, 29.1, and initial, so that's 16.4. Now always take a quick look that you get the reading right. Now here we count from top to down. Now the numbers are increasing, so that's how we read it. Don't make the mistake to by accident read in the wrong direction. Now this can easily happen with a burette, since it's the opposite as in a measuring cylinder. Now the reason is because we let liquid out, not filling it up. Now in a measuring cylinder we fill liquid in, so the numbers are increasing towards the top. With a burette we are putting the liquid in, but then what we're interested in is how much do we let out, how much do we add. Therefore the scale goes from top down, increasing. So volume of dilute hydrochloric acid added, so we just find the difference between these, and that is 25.4 here, 29.5 minus 4.1, that's how we do it. And here we have 29.1 minus 16.4, and that should be 12.7. So that's easy 4 points. Now just make sure that you have read the values correctly. Be careful here, not that usually gives you a lot of free points. State the color change observed in the experiment. So this is something new in the 2023 syllabus in terms of the indicator. In the old syllabus, it was phenolphthalein. In the syllabus that was used now, this has switched over to thymolphthalein, and thymolphthalein has a blue color in alkaline solution, and it switches to colorless in acidic solutions. Okay, state which solution of sodium hydroxide is more concentrated. Well, we can figure that out by checking the volume of acid that has been added to the sodium hydroxide, and we know we have added more in experiment 1, therefore our solution in experiment 1 is more concentrated. So solution A was a greater volume of acid was needed for neutralization or something similar. Deduce the simplest whole number ratio of concentration of solution A to concentration of solution B. This is relatively easily done. We know how much acid we have added, so we can just take these two numbers and divide them by the smallest number. So we have, these are the two volumes of acid that were added. 12.7 is the smaller number, so that divided by 12.7, and this divided by 12.7, and that is exactly 2, and this is 1, so the ratio is 2 to 1. State the volume of hydrochloric acid needed if experiment 1 is repeated using 10 centimeter cube of solution A instead of 25 centimeter cube. So here, what do we have to do? 25 divided by 2.5 is equal to 10. Therefore, we have to divide the volume of acid 25.4 divided by 2.5 as well, and that should give us rounded around 10.2 centimeter cube. Important here, it's a 2-point question, and the reason it is a 2-point question is unit. Whenever there is not a unit given in the answer, don't forget to write the units. Again, it's basically 3 points, but it tends to be forgotten. So always make sure that you write down the units when needed, when they're not given in the answer. In experiment 2, the conical flask is rinsed with distilled water. Suggest why the conical flask is rinsed with distilled water. And yeah, that is usually not to clean the flask and remove any residues, any leftovers from our experiment 1. The conical flask is not dried after it is rinsed with distilled water. Suggest why the conical flask is not dried. So the reason is we don't need to dry it because we are adding 25 centimeter cube of our solution A or in this case solution B. Now this solution B contains a specific number of moles of sodium hydroxide. Now if there are a couple of drops of water left in the cleaned conical flask, this will not change the moles of sodium hydroxide in our 25 centimeter cube that we are adding, which means it will not change the amount of acid that we will have to add to get to the point of neutralization. Also, that's what we can write. No, it does not change the moles of sodium hydroxide. So F, state the effect, if any, on the volume of dilute hydrochloric acid used in experiment 1 if the solution of sodium hydroxide is warmed before adding the dilute hydrochloric acid. Again, since heating it up does not change the number of moles of sodium hydroxide in the solution, therefore we will need the same amount of acid to neutralize it. The rate of reaction will be faster maybe, so the acid will react faster with the sodium hydroxide, but it will not change the total volume that we need to add. So there's no effect. And the reason is basically the same as the answer to the question before. No temperature does not affect the moles of sodium hydroxide. Suggest how the reliability of the results in experiment 1 and experiment 2 can be confirmed. No, this is a simple one as well. We just need to repeat the experiment and, very important, and we need to then compare, obviously, the results to make sure that they are the same. Suggest a more accurate method of measuring the volume of the solution in the sodium hydroxide. Now, this is actually a very common question as well. We can see that the student used a measuring cylinder to pour the solution into the conical flask. What is more accurate than a measuring cylinder? A volumetric pipette. Also very important that we write volumetric, which is a pipette that is made to pipette a specific volume. It will have like one, so they look a little bit like this, thicker or fatter at one end, and then here, this is the opening, and then up here the ball attached, and then here there will be one line, and that line could be specifically 25 centimeter cube. So that is a volumetric pipette, very accurate. Another possibility would be to use a barrette to measure the volume. Both of them are more accurate than a measuring cylinder. Aqueous sodium hydroxide reacts with aqueous barium chloride to form a white precipitate of barium hydroxide. Use this information to suggest a different method of finding out which of the solutions of sodium hydroxide is more concentrated. In your answer, state how your results show which solution of sodium hydroxide, A or B, is more concentrated. So again, what we can make use of is here in this experiment is that we get a white precipitate, which we can then filter off, dry, and weigh. Filter off, rinse with distilled water, dry, and weigh the mass. Find the mass, and then we can compare the mass between the two experiments or between the two solutions. Important here is that we would have to add an excess of aqueous barium chloride solution to solution A and solution B. And again, we would use equal volumes. So we use, for example, use again maybe 25 centimeter cube of solution A and B. Then we add excess, very important, solution. Then we filter the mixtures and rinse, dry, and weigh the precipitate, and mixture A will produce about double the mass of barium hydroxide. And therefore solution A is more concentrated. So this brings us to the question 3. Again, this question was much more difficult in the previous years because you were not given all of these tables. So I've added these tables to this slide here. Usually you would find these on the last pages of the exam, where you usually find the periodic table as well as an appendix. And yeah, you can make use of these tables to answer question 3, where we need to identify substances usually. So a student tests to solids C and D, tests on solid C. So solid C, we are told what it is. No? So usually we are told what one substance is, and the other substance we have to figure out what it is. So we have iron 2 sulfate. Complete the expected observations. The student dissolves solid C in water to form a solution, aqueous iron 2 sulfate. The student divides the solution into 3 portions. To the first portion of solution C, the student adds 1 centimeter cube of dilute nitric acid, followed by a few drops of aqueous silver nitrate. The observation, so we check nitric acid. Where are we? Just a moment. So we have nitric acid, few drops of aqueous silver nitrate. Okay, silver nitrate, there we go. So we can see that the test with silver nitrate is testing for the group 7 ions, the halide ions, chloride, bromide, and iodide. Since we do not have a chloride, bromide, or iodide ion in our solution, in this case, we would not see no change. No? So it's iron 2 sulfate, there's no bromide, iodide, or chloride in there. So we don't get any precipitate. No change, or maybe put this way, right? No precipitate. To the second portion of solution C, the student adds 1 centimeter cube of dilute nitric acid, followed by a few drops of aqueous barium nitrate. So again, dilute nitric acid and a few drops of barium nitrate. And this is test for the sulfate ions. So we can see that we will get a white precipitate. So that will be our observation. White precipitate forms. The third portion of solution C, the student adds aqueous ammonia dropwise and then in excess. So now we are probably testing for the iron 2 ion. So let's check iron 2. And we are adding aqueous ammonia. So we are in this column. So we get a green precipitate which is insoluble in excess, but the precipitate turns brown insoluble near the surface on standing. Okay, so it's insoluble in excess, which means that we get a green precipitate, which is insoluble in excess. Aqueous ammonia. Now, another way to write this is that we get a green precipitate forms, which remains after adding excess aqueous ammonia. So it's insoluble in excess. So yeah, we have the tables given here. So I think this is pretty straightforward. I would recommend you to go over a couple of past papers. You can use past papers from previous years, 2022, 2021, and you can just use the tables from the Specimen Paper 2023 and practice these questions a few times so that you know that you have an idea where to look in the table for which test. Practice it a little bit, but again, you don't have to memorize all of this anymore. You will have these tables in the exam as a reference. So, tests on solid D. Table 3.1 shows the tests and the student's observations for solid D. For test 2 and test 3, the student dissolved solid D in water. To form solution D, the student divides solution D into 2 portions. So, test 1 was done on the solid D. So, he did a flame test and he got an orange-red color. And we can see in the table orange-red color, flame test, that should be a calcium ion. So describe how to do the flame test. All right, okay. So we need to know how a flame test is conducted. So there are 2 ways. We can either use a clean wire and with a solid sample of D, and then hold it into a hot blue flame of a Bunsen burner, and then we observe and record the color of the flame. Another way to do this would be with a splint. A splint soaked in a concentrated solution of solid D, so we would have to make a concentrated solution of it, and then we can hold the splint into the flame. That works as well. Or a clean wire with a solid sample. And yeah, hold it into a hot blue flame of a Bunsen burner and then observe the color change of the flame. Identify solid D, so let's check out the other tests. So we already know that we have a calcium ion in there. Test 2, the first portion of solution D, added aqueous sodium hydroxide dropwise, then an excess. So first we got a white precipitate and no further change, which means the white precipitate is insoluble in excess. So we go back to cation. Effects of aqueous sodium hydroxide. We already know, pretty sure that it's calcium, and these results match with our previous flame test for calcium ions. Another test for calcium ions, white precipitate insoluble in excess, so that just verifies that we have calcium. And to the second portion of solution D, 1 centimeter cube of dilute nitric acid followed by a few drops of aqueous silver nitrate are added. We get a white precipitate, so that brings us back to our group 7. Halide ions, and white precipitate means we're dealing with chloride. So we have calcium chloride, not due to the ionic charges Ca2 plus and Cl minus. The correct formula is CaCl2, or we could name it calcium chloride. That is the identity of solid D. All right, and the last question in the paper is usually planning and outlining an experiment. So let's do this one together here. In this question, let's see, the label on a bottle of orange drink states contains no artificial colors. A scientist thinks that the orange color in the drink is a mixture of two artificial colors, sunset yellow E110 and allura red E129. Plan an experiment to show that the orange color in the drink does not contain these two artificial colors. Your plan should describe the use of common laboratory apparatus and samples of the two artificial colors and the orange coloring from the drink. You may draw a diagram to help answer the question. So the experiment that we will do here is something like perform a chromatography test or something like this. Then we can use the space up here to draw. So this is our chromatography paper. This is our baseline in pencil, and then we add 3 dots here. This is E110, this is E129, and this is the orange color, and we will maybe get something like this. Maybe the red one moves somewhere here, this one maybe moves here, and our orange one maybe, so this would be the solvent front, and our orange color maybe produces a result like this. And yeah, now we have everything already that tells us that our orange color does not contain the two artificial colors E110 and E129. Perform a chromatography test. We just do it step by step. What would we do? We would use a pencil to draw the baseline, add three colors onto the baseline. No, we actually should probably be more specific here. Add samples of E10, E129, and orange color on the baseline. Then something like put the chromatography paper in a solvent, where the solvent is below the baseline. And we can actually draw this here as well. So something like this. This is our solvent. We can see it's below the baseline so that it soaks into the paper and runs up the paper, but the solvent does not touch our colors. And then we wait, we allow the solvent to travel up the paper. And then we use a ruler to measure the distance traveled by the solvent front and the three colors. We calculate the RF value for each color, and compare them, and we will see that the RF values of the orange color or colors are Now, you don't have to split it up in two here, by the way. You can, because it's orange and it often mixes. There's a mix of two colors, but I think it's okay if you just draw 1 point as well. RF values of the orange colors are different from RF values of E10 and E129. Therefore, the orange color does not contain these food colorings. So that should be more than enough here to get our 6 points. And yeah, so this as well, these questions, I think they're pretty straightforward. They can be a bit intimidating because you have to write a lot, but in the end, yeah, it's just setting up an experiment. For sure, sometimes it can be tricky to have an idea of how to do something, but the best thing to actually be really good prepared for this kind of question is, again, have a look at a couple of past papers, check what kind of experiments are typically coming up, practice a few of these questions to answer them. You can do this by, I would recommend doing this by having the mark scheme right next to you for the first few questions, so that you just basically write it down following the mark scheme until you get an idea what the mark schemes want from you, basically what the examiners want from you. And once you've have an idea about the typical pattern of these questions, try to answer a few of these questions without the mark scheme, and then check how you've done afterwards. And once you've done this a few times, these questions usually become pretty straightforward and easy as well. So yeah, in conclusion, especially with the changes to question 3, that you are given the tables for the different chemical tests for the anions, the cations, gases, and flame tests. This paper has even become more easy, and I'm pretty sure you will agree that this by now is the easiest paper of the 3 chemistry papers, the multiple choice and the theory paper. All right, I hope I could help you. Hope I could give you some ideas of how to approach this paper, and I hope you've learned something new. And I wish you all the best for your IGCSE exams in the future and for your preparation. Until next time in my next screencast. Have a good day.